Welcome everybody. We appreciate you finding the time to join us here today for the first round of Live from Behind the Walls this semester. So before I hand you over to our host and moderator for today, Daniel Lucani, and all of our great speakers, I just have a few things to take you through. So first of all, this talk is being recorded and will be posted online later on, but of course we hope that you're gonna be hanging around, those of you who checked in. If you missed some of our previous events, you can find the recordings at the bottom of this page. That's the same page as where you registered for the event. And I would also like to present the organizing team. So this time, the organizing team consists of Daniel Lucani, who's a professor here at the Department of Electrical and Computer Engineering. And as I said, he will act as our host, moderator, and timekeeper today. And Hugo Macedo, who works as a research assistant here at the department. And my name is Lide, and I'm the community manager of Orbit Lab, which is also part of the department. And if you feel like it, you're welcome to present yourselves to each other in the chat. And to those of you not familiar with Orbit Lab, I just want to briefly tell you and show you that we are a tech and innovation hub and an open community for everyone with an interest in digital technologies and entrepreneurship. And as I said, we're also part of the department. So if you want to know more about Orbit Lab, you're of course welcome to reach out. So finally, we host a number of events throughout the semester. You're always welcome to attend. We're currently planning several events, and we hope to be able to truly invite you behind the walls in real life for future events. So keep an eye. Here's a list of the platforms where everything will be announced. So that's it from me. So I will now hand over this virtual stage to you, Daniel.
So thank you everyone for coming today, and particularly many thanks to Lide and to Hugo for helping us organize this, and of course for the support from Kasper and from Peter Gomez, and so which have been really great at initiating this series from Live from Behind the Walls. So many thanks for giving an opportunity to do this. And this particular set of talks, right? So is a result of the work from, financed by a number of foundations, right? So including the Danish Free Research Foundation, right? So the Innovation Fund, but also some European projects and also universities research fund. We also have some cooperations with a number of industrial partners, and it's impossible to do some of this research without their strong support. So just to tell you a little bit, so our members today, right? So most of them are part of our PhD and postdoc team at the Network Communications, Computing, and Storage team, right? So NetX. And we are a team that is actually looking constantly at what is next in networking for these different applications, right? And today the focus, right, so of many of the team members that you can see here is on aspects of data compression with very non-traditional applications, right? And the group is, let's say, led by my colleague, Associate Professor Shishang, and myself. And we have, as you can see, a number of PhD students and postdocs. And I'm actually pretty happy to say that several members of the team a week or two ago received the third prize and the second prize, some of them, for the Deutsche Telekom Challenge focus on wireless privacy. So it's actually kind of nice to be able to say that. So after a long commitment. So today, what you will see is that we have sort of a action-packed schedule, right? So we have a variety of talks, and there is a common trend, of course, that we pointed out. So it's this idea of next generation compression and data deduplication. And one of the things that you see is that there's a little bit at the beginning more fundamental components, right? So between theory and practice. Then we look at some aspects of how to use, how to be able to do analytics directly on compressed data. After that, there's a connection between, compression across a large variety of data sources and communication protocols. Then we have a big block that is actually looking at different aspects of compression and its implications on security and privacy. So in some cases, it's great to provide security and privacy. In some other cases, we see that there is, if left unchecked, it could have some very, let's say, problematic and nefarious leakage of information, especially if you're dealing with smart meters. And finally, there's some of our master students actually will be presenting a new take where we're using compression for data caching. So not collecting data and storing it, but actually the other way around, how to provide it. Having said that, so just a couple of basic things. So I will be turning off my camera during the presentation, but 1 minute before the time is up for the different speakers, I will turn it back on. If I say stop, please stop. All right. Questions, please do them in the chat, right? So we will continue the talks as we go. If you have questions for a specific speaker, just write the name of the speaker, the name of the title of the approximate title of the presentation, and ask your question to them. They will be able to then answer to you in that way. So with nothing more to this, I would just say that there's a couple of upcoming events in October 27th and November 24th. So please stay tuned. And if you have any questions on the research side or collaboration side, you're free to contact Lide or myself, right? So for this, okay. So I would like then, with no more to do, I would like to introduce our first speaker, which is Lars.
I'm going to present data storage when reality clashes with theory. And as stated, my name is Lars Nielsen. I'm a postdoc at the department here. So when we as researchers often present our results, we always celebrate the final success. We never present the carnage that can happen behind the scene. And that is kind of what I will be focusing on here. I'm not going to focus on presenting research results. The reason for this is that this is actually part of research that will be presented tomorrow at a conference. So I cannot share the full results here. The goal of our research, however, was to create a file system based on a new emerging technology that we call generalized deduplication, which aims to reduce the amount of storage that we use on disk. And I'm guessing some of my colleagues will go a bit more into detail about generalized deduplication, or at least I hope so. So the problem or the carnage that we hit was that we consistently ran out of disk space according to the commands we were calling from our file system. However, when we analyzed the tools that were, when we used disk analysis tools, we had ample space left, like we had 75% of the disk space left. So what was wrong? Well, there were two vectors we could attack to actually identify what was wrong. We could go for our own code, or we could analyze what is wrong outside of our code. We, of course, started with our own code because blame is mostly on us. And we did a full code analysis, and we followed all system calls. However, none of these revealed absolutely nothing. Instead, we actually had to look outside, and we had to look at the file system that we're using underneath our own file system called ext4. And what showed was it has something called a directory index. And what the directory index is, it's essentially an in-memory map of all the files in a given folder. And it is used to speed up lookup operations such as lsstat, and so on. However, this couldn't be a problem because according to the definition of the directory index, it should be able to represent just as many files as ext4 actually can. However, this is actually not true. When you look at the implementation in different Linux distributions, it actually has a limit. And it is even worse than that. That limit actually varies across multiple Linux distributions and even across different distribution versions. So what we observed was that Ubuntu 18.04, the desktop version, could have 12 million files in a single directory. The server version, 16 million files. Fedora desktop, 32. Fedora server, 32. Ubuntu 20.04 could have 20 million files. And Fedora 33, also desktop version, 64 million files. So there was no consensus about how many files a single directory could contain. And also, to be fair, like any sane person wouldn't store like 12 million files in a given directory, but we needed to do that for our research. So what are the solutions? Well, you can actually disable this directory index, and it would completely solve the issue. However, when we look up if a file exists or just want to stat it, it heavily damages the performance, and like a single lookup could take minutes and in some cases even half an hour. So let's hack our way around it was our decision and the end goal. And we kind of wanted to turn the disadvantage of the directory index into an advantage. The only problem is that quotation mark, it's a solution in the sense that we might still actually hit the limitation of the directory index. So the files we actually store in ext4 has a SHA-1 identifier. In binary, it takes 20 bytes, and if we convert it to a hexadecimal string, it's 40 bytes. And we decided, hey, let's use these identifiers to create a grouping system. And if we have the hash here, represented just by the indexes, we say that the two first elements that is shared by all files is a major group. So all files, just to specify, who has the first two characters the same of the hexadecimal representation will be in the same group. And then we said, let's go a bit further and say that those who share the next two characters are in the same minor group. So essentially, all of those who share the first four characters are in the same minor group. Based on this, we said, okay, let's create a folder structure such that all files that starts with 00 goes into the same major group folder, and then the following two, the red ones up here, that has 00 contains all that has 0000 and then whatever follows. By this, we create a grouping and can just write all groups that belong to the same minor group into the same folder, and therefore we reduce the probability of hitting the directory index limit. We retain the power, the lookup speed, and so on. We do this with minimum damage to the storage usage. It's roughly 4 kilobyte per folder we create at minimum. So this is the initial cost. It can increase. It has zero impact on the RAM usage, and it works also across ext2 and ext3, sorry, which are previous versions of ext3, and it works on ZFS. Another workaround that would actually fully work, but would cost a lot of RAM, is to keep a registry in memory and just disable the directory index. Then we would still be able to have the lookup, but it would increase significantly the RAM consumption of your file system. And in a real world scenario, you really don't want to have your file system playing Google Chrome and eat up all your RAM. And I think I went a bit quicker than I had intended, but thank you for your attention.
So our next speaker, I believe, is Aaron, that will be presenting his work on how to use analytics directly on compressed data. So please go ahead.
So as you can see, the title of mine and what Daniel alluded to before is that I'm looking at using compression to make analytics better. The title sort of alludes to two things there, that I've actually forgot a keyword there, but three things. That the analytics can be done more quickly through using compressed data. It is, of course, approximate analytics, since we're only using part of the compressed data, which I'll explain more in detail later. And thirdly, the last word there is that it's focused on the edge, or at least this presentation is focused on its use at the edge of IoT systems. Just a bit about me first, just to say hello. My name's Aaron. As you can see, I'm from Australia. The little blue cross there indicates where I come from precisely. I did my bachelor and master's degrees in Australia in electronic engineering. I worked for a few years at IBM and have now joined Aarhus University, where I'm doing a PhD. So the agenda for this talk is that I'll go through sort of an edge analytics framework that this analytics on compressed data work sort of fits into. As Lars alluded to and hoped for, I'll give a bit more information about the generalized deduplication compression algorithm. Then I'll go over how analytics can be done on top of that compression algorithm. Following that, how the compression algorithm itself can be tuned to better support that analytics. And then take you through some of the research results, showing that the compressed data is small, that the analytics is better, so to say, and also faster compared to alternatives. So without further ado, the framework that this fits into. So if you imagine your IoT physical architecture, you have your IoT devices, your temperature sensor, some machinery, or your smartwatch. At the far end, you have then the cloud infrastructure, typically where most of the data is stored, where the big workloads are carried out, and so on. And in the middle, you have your what's called edge infrastructure, the infrastructure that's generally more physically close in proximity to the devices themselves, but while more powerful than the edge IoT devices themselves, typically is somewhat resource constrained in itself, at least in comparison to the cloud. So a typical workflow might be that the data is collected at the devices, compressed, and sent to the cloud, where it's then analyzed. But to do that analysis, the data, of course, has to be decompressed. What we're proposing is that the compression is still done on the IoT device using the generalized deduplication algorithm, but the output of that is actually sent in two places. The basis, which is one part of the compressed data, is sent to the edge, whereas the remainder, the deviations, is sent to the cloud. In the next slides, I'll go into a bit more detail on what those exactly mean, but just bear in mind that the data is being split. The analytics then can be done at the edge using only a subset of the compressed data. So essentially, your real compression in terms of what's actually needed at the edge is even greater, because not only are you compressing the data, you're only using part of that compressed data. So how does generalized duplication actually work? I'll try to illustrate that with a pretty simple toy example. Imagine you've got some 6-bit binary data, and here I've just shown 5 samples so that it can fit on the slide. The way generalized deduplication works is it splits each sample into first a deviation part, which is typically the least significant bits. It doesn't have to be, but it typically is. But in general, the deviation is the part that varies most, has the most noise, and is the least, the fewest duplicates. The remainder then is generally the part that contains the most information, has the most duplicates. And that part is deduplicated. While the deviations were stored exactly as shown here, the bases, only the unique bases are actually stored. And finally, you need some sort of system for linking the two back together so you can decompress the data, and then we just have simple IDs for doing that. So in this simple example, you can see that we have got compression. The original data had 30 bits, whereas the compressed data has only 23 bits. That's a very simple, oversimplistic example, really, but you sort of get the idea that by having a relatively long base and deduplicating them, you can save a lot of data storage. So how do we then do analytics with that? To do that, I need to walk you through how we get to something called the base centroid, which is what the analytics is done on. So to illustrate that better, I'm using a two-dimensional example. So dimension 1, dimension 2, and then I'll take you through step by step how we get to that. So imagine a random data sample 16 and 15. The compression is done at the bit level, so we need to look at that in binary. So you can read that yourself. It's just converted to a 5-bit binary number. The binary number is then split into its base and deviation using what's called a transformation function. Simply just cut off some bits, cut off some other bits, put them to 2 different places. And here I've used the x's here to indicate what are the deviating bits. So for this given base, we then work out what the range is, range of values that can be assigned to that base. So imagine putting all zeros for the lowest value assigned to that base, and then all ones for the largest possible value that could be assigned to that base. And then likewise, what that is as an integer. And finally, the base centroid is the midpoint of that, or the centroid of that. And this is what we can then use for analytics. So imagine if we have all of our bases, then we can get a set of base centroids and use this as sort of a summary of the data, which is turns out to be quite useful for doing analytics. The last row here is called the maximum deviation. This is just the difference between, or the delta of that range that can map to the base. And this dictates how precise the analytics can be. If you have very large deviations or very large deltas in this range, your analytics is likely to be very imprecise and probably quite inaccurate. But the more precise it is, the better. And this in turn is then dictated by the transformation function. So in order to get good quality analytics, you also need to pay attention to what kind of transformation function you're using when you do your compression. Which brings us to the next point, which is how do we tune our compression so that we get compressed data that can be analyzed effectively. So to start with, we have sort of the default way that GD compresses data, or the way that it determines this transformation function or mapping between bits and then bases and deviations. So what it starts with is calculating the correlation between bits, using this as sort of a proxy for bits that are highly correlated and therefore have lots of matches between other bits and are good candidates for the base because they can be deduplicated, and correspondingly bits with very little correlation to each other, which are very noisy and therefore more suited to the deviation. So given that, a set of candidate base deviation splits are computed, and then it simply chooses them with the lowest compressed size. And what this gives you is very good compression, but often very poor quality analytics if you just want to do this kind of approximate analytics we've been discussing. So what we propose is adding an extra step here and using a classification heuristic to classify a given base deviation split as either likely to lead to good analytics results or unlikely to lead to good analytics results. We can then choose the configuration with the lowest possible compressed size that is expected to lead to good analytics results. And just a note that so far, the work that I've been doing is mostly focused on clustering, and in particular, the k-means clustering algorithm. But as I mentioned towards the end, we're extending this into other types of analytics in the future. Now, in order to find that find a heuristic, we looked at many different potential features relating to the data set, because we took the assumption that what transformation function will lead to a good compression analytics outcome will obviously not be the same for every data set. So we looked at different properties of data sets to see what would be likely to predict that. And what we found is that a very simple but yet effective heuristic could be made with just 2 features: the number of dimensions in the data set, and another feature we're calling the base ratio, which you can see here is the number of bases divided by the number of dimensionalities and the number of clusters in the data set. And just by breaking data sets down into low dimensional, 5 or less, medium, and larger dimensional data sets, we can have a rule for what the minimum base ratio needs to be in order to achieve good a compression configuration with good analytics potential. So for example, if your data set has 7 dimensions, it's necessary to have at least 15.5 bases per the product of dimensionality and the number of clusters. And you can sort of, I hope, understand this a little bit intuitively in that if you have a data set, the more clusters you have, the more complex the distribution of that data set is. And therefore, the better resolution you need, or the more bases you need to represent that accurately. Similarly, the more dimensions you have, the larger the volume of your data set becomes, and the more bases you need to cover that effectively. So how does it work in practice? Well, first of all, we are, after all, working with compression, so we'll start with compression and see how it performs in that. What you can see here is 8 different compression approaches. The bottom 4 here are widely known universal compressors. You may recognize a few. The top 4 are different combinations of GD. So we have default, which is using the default generalized deduplication configuration or transformation function, and then our heuristic. We also have up here edge, and then correspondingly not edge. And edge refers to where we just consider the basis table. And this is, I guess, valid since at the edge, if you're focusing on doing this approximate analytics at the edge, you only need to access the basis table. So it's sort of a shortcut in terms of compression, I guess. So the first one you can see under normal circumstances where you're not assuming you're at the edge and can just discard some of the compressed data or ignore some of the compressed data, we find that GD is actually fairly competitive with the best of the universal compressors. Using the default one, you can see that these box plots are pretty similar. The heuristic is not as good, but it's still competitive compared to some of the others. However, when it's at this edge configuration, it really shines. The default GD, as you can see, has a median compression ratio of 0.02. So essentially the data is 50 times smaller compared to the best universal compressor, where it's about 3.5 times smaller. Oh yeah, that was supposed to come up a little sooner to recall the configuration in terms of the edge. But another thing to note is that although the heuristic seems to be quite a lot worse than the default, this difference is actually primarily caused by one particular subgroup of data sets. Those being ones that have very high dimensionality compared to the number of data points. So if we are excluding this one relatively small subgroup of data sets, which to be honest are not very realistic for IoT applications, the difference between these becomes very small. But then in terms of analytics, probably the next most important thing. Again, just to stress, this is in terms of k-means clustering, and for that we measure the quality, I guess, of the analytics in terms of the sum of squared errors for the k-means algorithm. So the distances between all of the points and their corresponding cluster centers. And we define sort of we measure performance in terms of that sum of squared errors when doing the clustering on the bases, so on the compressed data, compared to doing it on the uncompressed data. So if we assume that analytics on uncompressed data is our gold standard. And what we find here, the blue line here is with doing the clustering using our compressed data, compressed using the heuristic method, compared to the orange one where it's using the default GD method. And as you can see, there's a massive improvement. So nearly 90% of the data sets we tested could be analyzed with an approximation ratio of 1.2 or less, compared to only 38% using default GD. In fact, it says here 25 of the data sets, it wasn't even possible to cluster using the default approach, since it just, by prioritizing compression, entirely just prioritizing compression, the number of bases was in fact smaller than the number of clusters. So quite limited there. And finally, in terms of runtime, another area where this approach shines quite well Again, we had 103 data sets, which we had in these different compressed forms. And what we measured was the time from going from compressed data to having a clustering result. So there's sort of 3 steps there. In the case of the universal compressors, the data had to be decompressed first, obviously. Then some parsing to get the data in its immediately decompressed form, or its stored form in the case of GD, into something that could be clustered. And then finally the clustering runtime. And as you can see here, the overall times are substantially better using the GD compressed data approaches. And the difference is massively driven by the clustering time. Why is that? It's the number of data points. Since clustering with GD is being done on the base centroids, there are substantially fewer points than if you do it on the entire data set. Some of these data sets had, for example, 100,000 data points. So if you're doing ordinary clustering, you'd be doing clustering on 100,000 data points, whereas they may only have 1, 2, or 3,000 bases. And therefore, you get a speed up of corresponding, whatever the ratio between those is, 30 times, 20 times, potentially more, given k-means is linear in the number of points. So yeah, you get a massive saving in runtime, and we haven't measured this specifically, but you can imagine yourself that this is also a saving in terms of memory. You have far fewer points that you need to store in memory and do clustering or other kinds of analytics on. So again, for an edge system, which is often somewhat limited in its computational resources, this is quite an advantage. So to sum up, what we've done is we've developed techniques for doing direct analytics on compressed data using the generalized deduplication compression algorithm, and also techniques for, I won't say optimizing, tuning this compression algorithm so that the compressed data is more suitable for analytics. We've shown that it has competitive compression performance, that the analytics can be done accurately, and that it can be done very fast. And in connection with that, with lower memory requirements to do analytics on the uncompressed data. A couple of next steps we're looking into are things like being able to run more basic queries with theoretical bounds, further optimizing this heuristic, and different kind of progressive or iterative approaches to this. I think that's all from me. I don't know if there's time in the break. No, questions before the end. So I'll call it there. So thanks for your attention and enjoy the rest of the presentations.
I continue with the presentation from Niloofar, and I can see that she's already getting things going. And this is actually focus on data compression, but looking at multiple sources of data, right? So, and how to do and its interaction with the, let's say, age of information, or how, let's say, old information becomes. So this is connected to issues of delay and latency, and how you can get improvements from that. So I will not say anything else. So Niloofar, all yours.
Yeah, hi everyone. Thank you, Daniel, for the introduction. Today, I would like to talk about multi-source lossless data compression and age of information analysis. By 2027, the number of connected IoT devices is expected to be more than 41 billion, which clarifies why the amount of data generated by these devices is of a great concern nowadays. And IoT devices are resource limited and energy constraints, which highlights the importance of reducing the amount of data generated by these devices and transmitted by them. Considering the fact that there's a high similarity between the data generated by IoT devices, for example, that if we consider the data generated by temperature sensors, we realize that multi-source data compression techniques have a good potential for compressing the data. So far, a wide range of lossy and lossless compression methods have been proposed. Lossy compression techniques are not suitable for some applications, for example, for compressing smart meter readings. And lossless compression techniques normally perform on individual devices, which means that they are not suitable for multi-source data compression. And also they do not perform well on short data, meaning that they require collecting and analyzing enough amount of data to provide a good compression. In the following, I will propose a new multi-source lossless data transmission compression method, which is suitable for short data, which is common in IoT scenarios. And I will analyze the age of information and compression gain for this technique. So I give a short introduction on age of information. Timely delivery of data is a concern in a growing number of applications, such as live video streaming. And age of information is a metric that quantifies the freshness of information. So let us take an example. Imagine that you watch football on your TV, and if a goal occurs at time T1, then it will take some time to transmit this information to your TV. So you will watch this happening at time T1 plus epsilon. In this example, epsilon is the age of information. In other words, age of information is the time interval between the present time and when the most up-to-date information at the sync node is generated at the source node. And one can say that online compression strategies can be used to reduce the age of information, but at the same time, advanced compression techniques require collecting and analyzing enough amount of data to provide a good compression, and the time required for collecting this amount of data can affect the age of information negatively. That is why we are interested to study that how our compression technique, how our data transmission protocol technique performs in terms of age of information. So my colleague already gave an introduction to generalized duplication, but I will also explain a little bit about generalized duplication. Generalized duplication is a lossless compression technique, which is proposed by our team in 2019 as an alternative to data deduplication. Generalized duplication compresses data not only by finding equal data chunks, but also by finding similar data chunks. So generalized duplication first breaks the data into equal sized data chunks, and then using the transformation function, it maps each chunk into a basis, which is the large part of the data, and a deviation. So if we consider the example in this figure, and we assume that each chunk is a figure which has a shape and a basis. And then we use a transformation function to map each shape into each figure into its shape, which would be the basis, and into its color, which would be the deviation. Then we can deduplicate the bases and we can reduce the amount of data because we don't need to compress, for example, the squares twice. So in this example, if we consider using data deduplication, we will see that we won't be able to compress the data using this data deduplication because the chunks are either different in shape or in color. So our goal here is to use the concept of generalized duplication to design a communication protocol which is suitable for short data. So our data transmission protocol, let us imagine that we have several source nodes and a sync node. One of the source nodes has a new piece of data, a chunk, and which is called A here. So we apply generalized deduplication at the source node to map our chunk into a basis and a deviation. Rather than sending the basis itself, the source node sends the basis ID and the deviation to the sync node. this spaces ID can be generated using, for example, a hash function, which is common across all the source nodes. Then the sync node checks whether it has the basis for basis ID or not, and since it doesn't have it, it sends a request for the basis, and by receiving the basis, it sends back an acknowledgement. Now, our source node has a different piece of data, a different chunk, which is mapped to the same basis, but a different deviation. And this time, the sync node has the basis for this basis ID. So the source node doesn't need to send it again. And now we consider another source node, which has a different piece of, a different chunk, but the chunk is mapped to the same basis. So when the source node sends the basis ID and deviation to the sync node already has the basis for this basis ID. It doesn't matter that this basis belongs to which source node. So all the data stored in the sync node can be used to reduce the amount of data transmitted by all the source nodes, and we don't need any coordination between the nodes. So the sync node sends back an acknowledgement, and we are fine. So that was our data transmission protocol, which I explained using an example. And I'm going to study the average age of information for our data transmission protocol. And to study average age of information, we follow the same approach as the one described in a paper by Zhang et al. In 2016. We consider a fixed to variable length coding because all the chunks are of the same size in generalized duplication, but the size of the encoded data varies. And we consider a constant bitrate between the encoder and decoder, or between the source node and the sync node. And we assume that one symbol is generated per unit time, while each chunk contains B source symbol. This means, so if you consider the figure on the right, the x-axis shows the time, and the y-axis shows the instantaneous status age. And we can see that at time B, one chunk is ready for transmission, and instantaneous status age increases. And then at time D1, we have a sharp decrease in the status age because the D1 shows the time that the chunk is received by the sync node. So we have new information at the sync node. So the average age of information is decreased. And sorry, the age of information has decreased. The factors that affecting the age of information are the waiting time, which is the time that a buffer is busy with transmitting another chunk, and also the service time, which is the time required for transmitting a chunk. And again, in the figure, you can see that, for example, our second chunk is ready at time 2B, and then it is received at time D2. For our third chunk, we can see that there is a waiting time, which is shown with W3, because our buffer has been busy still with transmitting our second chunk. So if we calculate the integral of this curve, then we can, and we divide this by the time, we can calculate the average age of information. So in this figure, we are comparing our technique, which is showed with GD, generalized duplication, with blue color, with data deduplication, shown with DD, and with LZW and deflate, which are standard compression techniques, and also with raw transmission of data. We are considering 4 real-world data sets, and we are considering 2 metrics, compression gain, where a higher value shows better results, and also the normalized average age of information, which is shown at subplot B. And we can see that our technique provides the highest compression gain for 3 data sets and performs as well as data duplication for the temperature data set. Our technique provides a compression gain of up to 5.18 for the Tuta data set. And in terms of average age of information, again, our technique performs far better than Deflate and LZW. And here in this plot, we are interested to study that if we change the size of a chunk, how this affects our results for Deflate and LZW in terms of compression gain and age of information. And the reason that we are interested is that previously we mentioned that standard compression techniques require analyzing enough amount of data to provide compression. And the number 1 here is the marker 1. Here, the number 1 close to the marker shows that we are considering the same data, the same chunk size for Deflate and LZW as the one that we are using for generalized duplication and data deduplication. And by number 2, we mean that the number 2 close to the markers, we mean that we are bundling 2 chunks together. And the same goes for number 3 and 4. And the ideal case is shown with the black square at the bottom left corner. And the closer that we are to the ideal case, we need better results. And we can see that by bundling more and more chunks and increasing the chunk size, the compression gain for Deflate and LZW improves. But at the same, this is achieved at the cost of average age of information. But so these 2 techniques have a trade-off between the compression gain and age of information, but generalized duplication is the closest point to the ideal case and provides the best results. Thank you for your attention.
All right. So thank you, Niloofar. So any questions, please use the chat. So, and I think now and I can see Gajraj already turned on his webcam, so that's great. And he will be talking about a very different type of compression now, still with a focus on the Internet of Things, but with this, as far as I understand it, and Gajraj will discuss this more, it's focused on a technique called compressive sensing. Gajraj, if you're ready, just please go ahead.
Yeah, hello. My name is Gajraj, and I'm PhD student under Professor Chi Zhang, and I'm working on secure data compression for Internet of Things. And in this, basically, I'm exploring compressive sensing to provide like joint compression and security. And I also explore like this compressive sensing can be used for compression as well as information secrecy and error correction. So in the final, I'll give a small demo that it can achieve all 3. The outline of my talk is basically I'll discuss about the compressive sensing first, and the existing schemes based on compressive sensing, and what we discovered that there are some vulnerabilities in the existing one. And then we propose 3 new schemes, so I'll discuss one by one. So as Niloofar mentioned that there are 41 billion devices, and as we can see, some of them are like continuously monitoring, used for continuous monitoring. So obviously they'll generate enormous data, and most of them are working the ISM band, and that is a limited band, has a limited bandwidth. And apart from that, the many technologies like Wi-Fi, Zigbee, they are working in the same channel, so there will be communication channel interference, so harsh communication channel environment. And the data which these devices capture or sense are confidential in nature, so we need transmission and storage secrecy. But for these all three problems, one can use like conventional solutions. For data compression, one could use like transfer coding plus entropy coding, or forward error correction. There are many best codes. And for encryption algorithm, one can use AES or GRAIN, or many string ciphers are there, so one can use them. But the problem with that is, suppose the device are resource constrained and they are battery operated. So the resource constraint here, what I say is ROM of size 48 and RAM is 10 to 32 kilobyte, and the clock is say 8 to 16 megahertz. And it has been like, from the researchers, it has been shown that if we implement these conventional schemes in these resource constrained devices, then the battery life reduces significantly. So instead of compressing data, in these devices, data is sent without compression. So the goal of the project is to provide end-to-end information secrecy, and in these devices is specifically targeted for these devices, and provide storage and data transmission efficiency, and the operations should be energy efficient. And I'm using compressive sensing, so compressive sensing based encryption schemes are designed. So in compressive sensing, in simple terms, is a matrix vector multiplication. So if you have an n-dimensional vector and you have a m cross n dimensional matrix, and this matrix has some special properties. So this is special properties. It is generated from Gaussian distributed or binomially distributed random variable. So, and the m is less than n. So we take a product and then we get a lower dimensional vector. So it provides dimension reduction. So automatically it gives us compression. And then recovery is performed using L1 minimization. So optimization algorithm is applied on Y, and the reconstruction is performed. And it is assumed that this signal is sparse in some transform domain. So to get the signal back, this transformation is performed. Now with this kind of compressive sensing scheme, it is shown that the mutual information between the X, the plain text. So now I'll call X as a plain text and Y as ciphertext. So the mutual information between plain text and ciphertext is equivalent to the mutual information of energy of the plain text and the ciphertext. So it says that the adversary can learn energy of the plain text. So we use this information and designed a decoding algorithm, and we asked two questions: that can compressive sensing provide like security, and what kind of attacks are possible on the general CS-based crypto systems. So we designed a decoding algorithm and then applied that algorithm on Gaussian and binomial sensing matrices based encryption schemes. So like this one is the plain text data, and after like encryption, we applied our designed decoding algorithm, and we were able to recover plain text information from the ciphertext. So we could apply ciphertext only attack. So here you can see that whenever there is this is the power average power difference signal. So whenever there is a power difference, our decoded signal gives us peak, and when there was no little change, it also gives us the recovered signal shows the little change. So it retrieves plain text information, not exactly, but it gives us some meaningful characterization of the plain text. To avoid that, we designed a scheme which we called energy concealment scheme. And we also shown theoretically that it is possible to achieve asymptotic perfect secrecy. So as I said that for the compressive sensing, mutual information between plain text and ciphertext is equivalent to the energy of the plain text and ciphertext. So we designed a transformation, and this transformation, it takes a signal from Rn to and sends it to a higher dimensional sphere, surface of a sphere, and such a way that the new vector has energy Emax. So this Emax can be decided by the designer. In this case, like if you look at this equation, so with this transformation, if the sensing matrix, the matrix which we use for compressive sensing, is taken from the Gaussian distributed, then the mutual information becomes I transformation X and given Yi, then information of Emax Yi. So in this case, the adversary could learn only Emax, and Emax is already public. We can, like, if suppose our plain text is in the range of say 2 raised to power of p, then we can decide Emax to be 2 raised to power of 2 and p. So that is publicly known. And to materialize this energy concealment scheme, we use LFSRs to generate the sensing matrix, and this is the signal plaintext, which is given to the EC, which is added with the EC variable. So that makes a constant energy signal. So XEC is a constant energy signal, and sensing matrix is generated based on key and the initialization vector, and same because this is same as symmetric key encryption scheme. So at the receiver side, same key and IV is transmitted with the ciphertext, and key is shared with the receiver. So then this matrix and vector multiplication is performed, and this is transmitted to insecure channel, and then from YEC plaintext is recovered from the knowledge of phi, and the EC variable is removed because it is not required. And based on this EC variable, we also designed a new signal quality measure. So like if there is a noise in the channel, then one can decide that to keep it or to remove it. There is no extra, like CRC and other information is not required. And we also designed a decoding algorithm based on EC variable, which improves the reconstruction quality. And we shown that the ciphertext attack and known and chosen plaintext attack or related key attacks are not possible for this scheme. And this scheme falls in the joint compression and encryption category. And we also implemented this whole scheme in telescope mode, the same hardware specification, using quantity NG, and these are the time measurements. So if we use AES, it takes around 110 millisecond, and then this is the uncompressed data transmission. And if we use EC scheme, it reduces the encryption time as well as the plaintext transmission time and the data transmitted. So we gain in both, like in the encryption time as well as in the transmission time, and the transmitted packet is also smaller compared to the AES case. And we also explored, because to avoid other attacks, there was one more scheme which is called energy obfuscation scheme, and we applied the designed attack decoding algorithm on using this cameraman image. So this is the reconstructed image from one-time sensing. So one-time sensing here means that the sensing matrix is changed for each sensing. In this case, like you generate a sensing matrix. If there is a change in plaintext, you send a encode with a new sensing matrix. And both the schemes are vulnerable, which we have shown. And then our scheme do not leak any information. So from here, it is visible that the contour of the image is visible. Same for the other scheme. Then we designed a another scheme which we call multi-class privacy-preserving cloud computing scheme. So I'll go to, and this is based on compressive sensing. So here, suppose there are two users, one we call super user and another one is semi-authorized user. So super user can recover the whole plain text and semi-authorized user can recover statistical information or the information which is not sensitive. So again, here the compressive sensing is performed by sensing matrix, which is, and the here we have done one more thing. So super user and semi-authorized user, like in normal compressive sensing, the decompression algorithm requires optimization algorithm. So that is transferred to cloud. So encoding is performed on the plain text data with some R and P. They are key based on super user and semi-authorized user, and that is transmitted to the cloud, and cloud decompress the data and it transmit R into PX to super user, and the semi-authorized user and adversary also receives the same information. And we have shown that this is not able, adversary is not able to recover X from this combination. And super user can recover the complete plain text, and semi-authorized user, based on the key specification, it can recover that part. So we have shown two scenarios. So at the one scenario, so this is the power readings, smart meter readings, and so this is the reconstructed signal at the super user. So super user can recover the perfect, and the semi-authorized user gets the permuted entries, not the exact entry. So semi-authorized user can recover the mean, variance, and histogram, this kind of information, but not exactly from which house these readings are coming, or that is semi-authorized user will not be able to recover. And the reconstructed signal at the cloud is completely different. We also saw application of this scheme for data anonymization. And in this case, we consider image to be in two parts. Suppose the part with the face is called sensitive region, and the image without sensitive region, non-sensitive region. So for semi-authorized user can recover the non-sensitive region. So like without face, so this image reconstructed at the semi-authorized user, and this is the image reconstructed at the super user. In the normal case, there's like if we, for the AES, it has to be done in two times encryption, but this is scheme, it is done in the single operation. Then we designed a scheme which we called INCRUST, error robust compression and encryption scheme. And in this scheme, we saw that theoretically, and we also implemented this one in TLSP mode, and so that the three fundamental functions of communication channel, they are compression, encryption, and forward error correction, can be combined and implemented in a resource constraint device. So the current resource constraint device have only option for encryption and very low level of compression. But using this technique, one can combine all three functions in a single matrix operation, and then it can be performed. So it gives us like compression error recovery at the receiver, information secrecy, and reduced complexity. And we proved that if we take two metrics, A and B, from some Gaussian distributed, or it can be a plus minus 1 also. And then if we encode with Y, then if this Y is corrupted with the channel noise, then again from this YE, X can be recovered. So we take an example of ECG signal, and then these are A and B metrics are sign metrics. So this is ECG signal, and then this A and B matrix are binary matrix plus minus 1, and then I construct a G matrix that is A into B, and then this is encoding is performed to only single matrix and vector multiplication, and that is transmitted. Then this is the transmitted one. Then I generate error signal, and I add into the transmitted one, and then finally I recover the signal recover the error, and then that recovered one removed from the received Y vector, and then finally the signal is recovered. So it performs both. It recovers it. It basically, if we look at this example, we have converted a dimension of 256 to 180, and it provides both compression as well as encryption. So that if we also compared this scheme with AES and RS, so we use AES for information secrecy and RS for error correction, and we use our own scheme, and with a different like interference rate. So this is with the RS and AES recovered, and this is for the encrust recovered, and similarly for the higher interference rate, the image quality degrades further. And for us, this is the PSNR of the reconstructed images with the interference rate. So for AES RS, it drops sharp drop, and for us it is encrust. It goes very slowly, and so it provides like error robustness with soft thresholding. And these are some of the papers which are I published. From that, I have presented my work, and I end my talk, and I'll be happy to answer if there are any questions in the chat. Thank you.
All right, thank you, Gajraj. And I think now we will have a different take, right? And we will talk about compromise by compression. This is Marcell Feher, which will be talking about this. So Marcell, the floor is yours.
All right. Welcome everyone. So the talk on the title of my presentation is Compromise by Compression. The context of my research, as basically everyone else before me, is IoT data. So mostly I will be talking about what happens when we start compressing information that is coming out of some kind of IoT sensor, compress it, and where's the information leak, what unexpected issues might occur. So first, let me start by a couple of motivation slides. So why do we have data compression, and why is it good and necessary for Internet of Things? It's very simple, really. With Internet of Things, the data growth is predicted to be exponential. Actually, we are already very much in it. So it's not a prediction anymore, but we are seeing really that it is indeed exponential with all the sensors that are out in the world. We see how it actually changes the amount of data and the amount of capacity needed from our infrastructure. So the obvious, what happens when we observe exponential data growth somewhere? The obvious and very expensive solution is to try to scale the infrastructure in the same manner, which is often very expensive and in some cases basically impossible to scale the infrastructure in the same way. So a better approach is to try to increase the efficiency of data transfer and storage. So use our existing infrastructure in a better way, or at least try to break down the growth rate that is necessary for the infrastructure to follow the exponential growth rate of the data itself. And data compression is an excellent tool in this task. It can be applied completely transparently, so we don't have to redesign all the protocols, all the data formats, all the applications. We can just use data compression on the communication channel or the storage, and the applications or the layers around it doesn't have to know anything about it's happening. Also, if you don't need full control, if you don't need full precision of the data, then one way to do data compression is to do lossy compression, which results in much better compression rate at the expense of giving up some of the precision. In some use cases, this can be allowed, and then data compression can be an even more powerful tool than it would be in a lossless way. Since IoT data is very highly redundant, it's actually a really ideal, really good ground for data compression. Compression can be used in different scenarios, not only with IoT data, but IoT data happens to be very, very compressible. Also, compression is not only used for data transmission. It can actually improve all three parts of the data lifecycle. So transfer is faster, and we need less energy to do it when there is less bytes to be transferred. In terms of data storage, we need fewer disks, or on the same amount of disks, we can store more data. And as we have seen previously, it can even speed up analytics by running queries or running different algorithms directly on the compressed representation. We can either get much faster results for these queries, or in the same amount of time, in the same amount of memory, we are able to process and analyze much more data if we found ways to do the analytics directly on top of the compressed representation. So data compression in general is a tool to try to represent the same information with fewer bits. And over the decades for now, really many techniques have been developed to try to find redundancy and try to remove this redundancy from the data itself. Compression is not a special method that is being used only in a couple of edge cases. It has become a fundamental technique that is used basically everywhere in data transmission and storage. If you first look at data compression, it seems like it has only advantages, really. It's completely harmless. It can compress the data. We can have miraculous advantages of compression in all parts of the data lifecycle. So what could go wrong? Can anything go wrong with it? Is there any issues with using data compression? So everything seems to be perfectly fine and very nice until 2012, when the so-called crime attack was published, which is an attack on a compressor that works in web browsers and part of the TLS standard. And with this attack, the attacker is able to steal session cookies of the users from their own browser. So a few things about how it works. Obviously, I won't be able to go into details with the crime attack, just a high-level overview. So almost all web compression, so compression that is applied on web traffic, is based on the so-called deflate algorithm, which similarly to all the other compressors basically works in a way that if there is more redundancy in the data, then larger and larger chunks can be like deduplicated or can be removed from the compressed representation, which results in a shorter message. So more redundancy, shorter message. In terms of the crime itself and the TLS protocol and web traffic, the way it works is the following. So when a browser sends an HTTPS request, then basically it takes some input data, which can be like the form, the contents of the form that you filled, or just the address, the URL of the page that you are trying to load, and combine this with the cookies that are stored by the same website where the request is going to. That's how the cookie system works. It takes these together, compresses them, and then encrypts them and sends it over the network. So the crime attack works in a way that the attacker controls the input, so basically the contents that we are combining together with the cookie and trying to send. So the attacker has full control over the input, and they are able to observe the message size at the end. And the method itself is trying from very small inputs, very systematically try to do this. So control the input, change the input in a systematic way, and then basically observe the size of the message that goes out in the network, and try many different inputs. Since the compression is used on top of the input and the cookie together, if this observed size gets smaller, so basically the attacker would establish a baseline and see how this compressed message size changes with different inputs. When this size gets smaller, then basically 1 byte of the cookie is revealed. once the whole cookie is revealed and the attacker has your session cookie, they are basically able to impersonate you as a logged in user towards the service that has been compromised. So it's a really serious issue. There are multiple ways to do it. There are different like algorithmical challenges that needs to be solved. The best crime implementations from a couple of years ago, they needed in average six requests to decrypt a single byte of a cookie. And cookies are generally not that huge. So in a couple of hundreds of requests, they were able to steal your session cookie. When it was discovered, crime worked in both Chrome and Firefox, which at the time made up approximately half of the browser market. And it also worked on approximately 40% of the biggest, most prominent web services like Dropbox and GitHub. A lot of time has passed since then, so crime is not really a realistic problem right now, but there was no real solution for it. It compromised a part of or it exploited a part of a compression method that was part of the standard. So the solution for crime was to turn off actually compression for that particular part of the TLS communication that was vulnerable for it. So if someone knows how exactly a compressor works and has some side information or some other capabilities, like being able to control the input, then there are actually real problems, real life problems that might come from compression. My PhD research is a little bit different. What I'm working on is so-called privacy-aware compression of reported electricity usage. What we are talking about really is there are smart meters in the homes, in your homes, that are measuring your power consumption and sending this information periodically to your electricity provider, your electricity company. And this data is also getting compressed. What I'm working on is trying to figure out whether this compression reveals something about your power consumption use and what are the implications of that, and how we could design new compressors in a way to decrease this information leak and increase more privacy, and also how to create new compressors that are more in line with the newest data trends in this world. So you might be asking, so what does the power consumption reveal? Where is the private information in my power consumption? Actually, it turns out that it reveals quite a lot. For example, if an attacker would know only a single number per day of your complete power consumption, like the total kilowatt hour number, for example, every day, then they would be able to very easily figure out, for example, when you are on holiday or which days you work and which days you don't work. If you go a bit higher in resolution, if an attacker would have access to the 15-minute resolution readings of the power consumption of your home, then they would be able to figure out what time, like what's your daily routine, what time you go to sleep, what time you wake up, go to work, and what time you arrive home. So basically during the day when the house is empty. It would be very easy to say, but they're also able to infer, or at least have an educated guess about how many people live in a household by looking at the maximum electricity levels, the power levels that are consumed throughout the day. And also from the same information, they can guess or make an approximation of your social status, like what kind of devices you might have in your home. If we go with even higher granularity, sub-second sampling of the power consumption, then there are scientific papers that show how to reveal or how to infer which TV channel you were watching just by the high granularity, high frequency power consumption data. So actually there's a lot of private information that is included in these smart electricity meter readings. What is typical right now is that the smart meters record a reading every 15 minutes, which include the past 15 minutes power consumption, and they locally aggregate these readings, or collect these readings in their internal buffer. And once a day, typically around midnight, they upload the 96 readings that take up 1 day of these power consumption readings. So there are two problems that might occur. One is how much is an attacker actually able to reveal from the contents of the message? And the other is how does this change? How does this amount of information change with the frequency of the upload? So is it worse, and how much worse it is if we upload these readings more and more frequently? So first, let's take a look at the contents of the message. So obviously, electricity companies don't send this information around in plain text. There is encryption of these messages that are being sent, so a number of readings are like bundled together, and before they are actually sent, they are uploaded to the electricity provider. There is an encryption stage. However, it turns out that an unfortunate combination of the used encryption method, the data format, and the compressors that are being used right now, these still allow attackers to infer or try to learn patterns of electricity usage of consumers only by observing the compressed size of the readings as they are being uploaded from your smart meter to the electricity company, without having to steal anything, without having to hack any encryption keys, and even without being able to monitor the network as it is happening. So if they are able to compromise logs, for example, like a month, 2 months, or a year later, they are still able to infer this information from past logs. They don't have to be there present in real time when the smart meter is uploading. The other issue is, or the other dimension of this problem is how frequently data is uploaded, and how much information can be gathered from it, and how much worse does it get if we upload this information more and more frequently. And the trend here is that electricity providers want to have more up-to-date information, basically, for a lot of things. So to be better in load monitoring, prediction, they have many business goals that are helped if data is coming not once a day, but much more frequently than that. Obviously, if data is uploaded more frequently, then the information leak that is present in the channel or in this data upload system also becomes higher and higher granular. So if you remember, with 15-minute readings, an attacker theoretically is able to figure out what's your daily routine, what time you would do things, how many people are in the household, what's your approximate status, and so on. And unfortunately, the trends of this world is going towards more and more frequent uploads. So giving more and more opportunities for an attacker to learn about your habits and what you do and when you do it. I'm running out of time, but that's all right. So what can we do about it? For the whole industry, this is a new problem. First of all, because the industry is shifting towards uploading things more frequently. And second, the compressors that are being used now that can be compromised only by the compressed size has been designed basically a long time ago with the assumption that the whole days of data is going to be uploaded at once, at least. So the action plan is basically discover the problem, which has recently been done, determine how bad the problem is and with the current compressors and how much worse it's getting if we start uploading things more frequently. And obviously the solution is to try to either fix the current compressors or design new ones specifically for these new challenges that we are facing. And my research results is partially, at least, to first of all, to determine the severity. So I have written papers in that direction to actually quantify how much information is being leaked and what an attacker can reveal. And second is to propose new compressors that significantly reduce the correlation between the size of the compressed messages and the actual power measurements that are encoded in them. And they also offer better compression than the old compressors with more frequent uploads. Right, so basically the new technique, or the core of the new technique that we are using is that in comparison to the old compressors or the current ones that compress each packet separately and therefore is quite predictable, we are using information that has been sent in a previously compressed message, and therefore almost completely removing the correlation between the next packet size and the information that is encoded in it. And we also help with with the issue that an attacker cannot just start listening anytime or cannot acquire logs from any time period and start using it immediately, since all these packets depend on the previously sent messages. If they are not there from the beginning, there is not much information that's possible to extract. My final slide. So on the top, we see a sample of a power consumption chart, and with different compressors, how does it look like on the wire? So the compressed size of the messages that are being uploaded. The last one is our proposal, which only changes the size when there is significantly new information being sent from the beginning of the time window. And on the lower the lower chart, we can see that the compression ratio of our proposed method, which is also the green one, is significantly better with these more frequent uploads that we are going towards. All right, thank you very much for your time.
All right, great. Thank you, Marcell. And we are 1 minute late now, but it was there was a slight change of plans and agreement between Hadi and Marcell, so they shifted 5 minutes between each other. But Hadi will now present his work on dual deduplication. So Hadi, take it from here.
Hello everyone, my name is Hadi Sehat, and I want to talk about a brand new method of deduplication called dual deduplication and go through its theory and possible use cases. So, is it okay? So today's main area of focus was about compression, especially in systems like cloud storage, and it's also the same for my line of research. So in a cloud storage, we have some struggles for both parties, the cloud and the clients who wish to use the cloud as their storage. The cloud, of course, wants to perform compression on the arrived data. And this compression can have many different algorithms and protocols, one of which is deduplication, or more recently improved, called the generalized deduplication, which removes the duplicates of data in order to compress and reduce its size. But the client is also worried about the privacy of the data it uploads to the cloud, which means that it doesn't want sensitive data to be revealed to either cloud or any other potential attacker that can attack the cloud in any possible way. However, there is a big trade-off between the ability of cloud to compress data and the privacy of the clients. Where does this trade-off come from? We need to take a deeper look into how the deduplication and generalized deduplication works. As the name suggests, generalized deduplication works better and has higher compression rate when the data is more similar and homogeneous. Which means that the cloud, of course, wants to receive raw data. For example, if you have temperature data, the cloud wants to receive the temperatures which follow a certain pattern and follow a certain probability distribution, and therefore are easily compressible rather than an encrypted temperature, which in cloud's eyes is random nonsense. However, if the client uses cryptographic privacy in order to keep its data private, it maps data into a more random distribution. As the more random this data looks in the eyes of the adversary, the better our cryptographic algorithm is. So we have to find a way to encrypt our data in a way that it's still secure and keeps our data private, but doesn't reduce the compression potential in the cloud. There have been many algorithms suggested over the years, starting from convergence encryption in year 2004 to Dopeless, Duan's scheme, and BLS convergence encryption more as recently as 2015, all of which fall into the category of message leaked encryption. However, all this category has a big problem that they are server aided and require a trusted server or a dealer if we don't trust the server. And if the server crashes or the dealer crashes by something, the algorithm will completely stop and we will lose all the data. Also, the convergence encryption and doublets are exploitable by brute force. And if we want to solve this, we have to make it a more complicated algorithm, which are either not applicable for long-lived data, which is the case in Duan's scheme, or it adds a huge communicational or computational overhead on the client, which is the case for BLS convergence encryption. The most recent breakthrough in this case is actually done in our group by Daniel, Lars, Rasmus, and other people, which is called multi-key revealing encryption. Now, this idea and this encryption actually works, and the main idea behind is that to leverage Hamming codes to map different data into the same chunk, so that all this data will be mapped into a same base, and we store deviations in order to show what the original data was. And by doing this and sending the bases to the cloud, we introduce uncertainty for the cloud, so the cloud will not know which data it actually was. It can only guess based on the information that it has and the bases that map, then the files that map to that particular base. However, this method uses a random oracle to prove its privacy, which holds some assumptions. So we assume that some things are, for example, mathematically cannot be broken in real time in order to prove that this particular protocol is private. So here comes the question, and that do we really need to use cryptography to ensure our privacy, or there are other methods that do not include assumptions? And the answer is yes. We can use information theory and the tools that it provides to us in order to ensure privacy. So our idea here is to use information theory, but which part of information theory we use? We use deletion channels. Now, for those of you that are not familiar with deletion channel is a type of a channel between a sender and a receiver that when sender sends some data, for example, in this, to example, a series of bits, some bits along the way got deleted. And the receiver will receive something that is shorter than the original data that the sender sent. Now, some facts deletion channel is a very hard problem for the receiver to actually retrieve the original data. And as a matter of fact, the capacity of deletion channel is still an open problem in 2021. So we want to leverage this problem and use it in order to introduce a privacy into our cloud storage system. So we use deletion. So the whole idea behind that is that I have a file which I call here raw data in our client. We delete some elements from it. We generate a base which is going to be sent into the cloud, and then we store the deleted value and the pointer to its position locally into the client. Therefore, a base which is still a huge chunk of data will be sent to the cloud, and then the cloud will take care of it by performing whatever deduplication or compression method it was using. And by saving some elements of the original data, I introduce uncertainty to the cloud and I ensure my privacy. So how does this uncertainty work, you may ask? So the cloud sees something like this, 30722. Now it wants to guess what the original data is. So it can be 301722, where the client deleted element 1 in position 2. It can be 307252, where the client deleted element 5 in position 4, none of which are the actual raw data. So the cloud can only guess. And even if it has information about the original file, it can be an educational guess, educated guess, but it's still a guess. So it's not 100%. Therefore, we have privacy for our files, and the cloud can still perform the deduplication. So we live happily ever after. But yes, the answer is this will work, as we will show you in the results. But we can improve this scheme by multiple ideas. But before I go through the ideas, let me go through quickly at our system model. So the system model is a cloud client. The client uploads and gets data from cloud, and the cloud compresses the received data and decompresses if it wants to send the data back. The most important variables in the protocol that we want to discuss is compression rate, which is the required storage divided by the total storage before compression, and the uncertainty, and we define uncertainty as the Shannon entropy that the cloud faces after receiving the outsource. And the metric that we use is leakage, which means that the change of entropy of the original file in the eyes of the cloud after receiving the outsource. In this work, we add another part to our cloud client environment, which is called policy. So remember from what I told you a few slides back, that the cloud wants to receive data that is homogeneous as possible. And the client wants to delete some part of the file, and we want this deletion to perform in a way to ensure this homogeneity. So policy here comes into the picture. Policy is something that is sent from the cloud to the client before the client wishes to upload. So it's some kind of a handshake in a sense. And it contains the chunk size, which is the size of outsource that it wants to receive. So it kind of tells the client how many elements you can delete, and the probability distribution of the symbols that it wants to receive. So the client will delete the symbols that have the lower probability distribution in the probability distribution of the policy. So this is the whole idea of the policy. Now let's see about the client. If we want to do deletions in the traditional way, I need to store position and value for each deleted element, which is a huge chunk of data. Instead, we have idea that determine the positions by a random seed. So we use a pseudo-random number generator, and we use a seed to which determines the position. So I only need to store the random seed and the values. However, using a random seed may interfere with the policy that we want to hit. So in order to solve this issue, kind of solve this issue, we generate a total of tau seeds, where tau is a system-wide or a client-wide constant, which tells me how many possible outsources do I generate. After generating the seeds, I delete the elements as the seeds told me. So I generate a total of tau possible outsources. Then I use another information theoretic tool, which is called inversion, in which I invert every bit of the created outsource, so every 0 to 1 and every 1 to 0. And this will create a total of tau new possible outsources. Then we calculate symbol frequencies and choose the closest outsource that has the closest symbol frequency to the probability distribution. In this work, we consider closeness. The notion of closeness is the Euclidean distance. As a toy example, let's say I have this original data F, so I generate two seeds. Let's say tau is 2. They give me positions. I generate two outsources based on the positions and create deviations, seed and the values. Then I created the inverted outsources, which share the same deviation except for a bit that indicates if it's inverted or not. And then I calculate the Euclidean distance between the symbol frequency and the probability distribution indicated in the policy, and I choose the one with the lowest value, which in this case will be outsource f prime 1. So f prime 1 will be sent to the cloud. I lost everything. Yeah, and the deviation will be stored locally. And in the cloud, I want to perform the duplication. So traditionally, I would have to do brute force search to find the duplication. But again, remember that we had probability distributions. So So an idea that here comes to mind is to sort the symbols. So we group the symbols, sort by something called bracket ID, and then store a symbol ID to indicate which symbol is that. We can improve this even further by reducing the symbol ID for the symbols that have higher frequency using Huffman coding, and even improve this further by eliminating the lowest probability symbols which have bigger symbol IDs and changing their value to a highest symbol ID. Now, in 1 minute, I'm going to rush through into the application in the cloud. So the cloud receives some outsources. What? Yeah, okay. So I rush through even faster. And in the results, we can see here is the leakage that we have for our method for different values of NO, which is the size of the file, and MB, which is the size of the base. And we can see that we are normally hiding about 40 to 50, 20 to 40% of our data. And while hiding this amount of data, our compression rate is nearly around 50%. Now, if we compare our work with other works that provide some kind of security by using generalized applications, SecDedup, as you can see, has very poor compression rate. Yggdrasil is SecDedup with deletions in the client. So you can see that here I have a huge gain in the compression, but we improved this by using random seed and by using the new protocol in the cloud. We are close to Brotli, which is a very well-known and widely used deduplication method, but we can't still beat it. But it needs to point out that Brotli doesn't have any privacy while our work does. And our work can still be improved as it's a very new idea. And I'm going to stop now, and thanks.
All right. Thank you, Hadi. And we are a minute or two late, so Anas or Christian. Anas will be presenting.
Yeah.
So please share your screen and go ahead.
So the other guys talked a lot about this generalized deduplication, and we during an R&D project on our masters last semester we tried using it in the context of data caching. So basically we'll just go through the motivation for that project and the system model, what we implemented, and then talk about our measurements and results and what we've continued to do on our master's thesis this semester. So basically, the motivation for using generalized deduplication in this context is to be able to better utilize the cache because we can store more data in there, and desirably also lower the access time of the content. And in investigating this, we tried comparing it to various other state-of-the-art caching schemes, such as just basic full file caching, but also ordinary deduplication and erasure-coded caching. And our analysis focused on the cache hit ratio, and we did some purely analytical work on the access times. So basically, we had this very simple system model where we have a user or a client, and we have an edge which implements an LFU cache for these chunks that are deduplicated, and it stores some metadata in an SQL database. The files that we're actually requesting are stored on the clouds, and all the communication went through REST APIs. Because the project was limited in time and scope, we didn't have time to actually implement the general deduplication schemes in our project. So what we did instead was that we generated data that looked like it had already been through the transformation function. So we generated some base and some deviations. And what the figure down here shows is that when we could model this data according to some different standard deviations, and the higher standard deviation, the more variation there was in the data. And basically the figure attempts to show that the red one here, which is the generalized deduplication, has a significantly higher chance of the same or a similar chunk occurring. For the system, for implementing it, we used Python, which was also kind of a blocker for really getting to use the real transformation functions. Besides that, we used Docker and Docker Compose to be able to really very fastly start and restart our test environment. And for each of the testing setups we ran almost 400,000 files for 4 setups. So that's about 1.5 million files we requested in total.
Yeah, and the results were that, well, this first plot shows how the standard deviation of the files requested affected the cache hit ratio. And as expected, we can see a drop in the utilization ratio when the standard deviation of the files requested increases. And the nice thing to notice is that especially the generalized deduplication scheme seems to show its promises when the standard deviation of the files requested increases compared to the others. And this is, of course, due to the fact that there won't be as much effects as the others as long as there are these similar bases. If you go to the next slide. Yeah. So when we look at how the cache size affects the utilization ratio, we can quite clearly see that all of the schemes benefit from having a larger cache. However, there is the generalized deduplication scheme, which seems to have a higher benefit, and it is especially clear when we see that the standard deviation is quite large, as we see on the right-hand side plot. And if we take both the cache size and the standard deviation of the files requested into account, and we could do these 3D plots, and it may be a bit hard to see, but the take-home measures is basically that the generalized deduplication case seems to have a higher cache hit utilization ratios, and it doesn't drop as fast as the others. The next slide. And as Anders briefly mentioned, we also did a analysis of that we haven't explained much in depth here. What we basically did was that we introduced these 2 variables, alpha and beta, which is the relation between the transmission rates and or the latencies between the clouds and the edge, or between the edge and the user, and between the edge and the user. And if we use these values and our measured cache hit ratio and some rough mathematical model of the access times for the different scenarios, we ended up with these results we can see here. So in this model, we had to fix some values, of course, to be able to plot something, to do these control plots, and the uppermost plots, we can see the relationship between this alpha value and the cache size. And what we can see here is that if we compare generalized deduplication to the ratio code case, we can see that the generalized deduplication is faster at reaching lower access times than the ratio coded ones. And this is also visible when we compare alpha and beta on the y and x axis to the access times. Yeah. So naturally, our results is very much based on this part that we generated data ourselves. So the next step for us is to verify these promising results about the generalized deduplication in a caching sense. So what we are about to do in our master thesis is actually to implement this in a real system with real data, and use generalized deduplication with some different transformation functions, and not only rely on an analysis. And based on this system, we will measure some access times with different setups, and hopefully these will show the same promising results. Yeah, I think that's it.
Thank you, guys. And I think we are actually back in time, in good time. So thank you for that. Well, just to close up, right? So I wanted to thank you all for being in this sort of live from behind the walls program, right? So, and hopefully, there was something interesting in some of the talks that that caught your eye or that you would like to discuss further. And if you do, make sure that you reach out, and of course you can reach out directly to the different speakers, but if possible, I would suggest that the inquiries regarding research come to me, and then I can very easily point you to the right direction. If you have some interest in presenting your work in a future event, please contact Lide. So she's organizing all of this, all of the logistics of this talk. So, and she will make sure that it's that you're included in some way. So. Again, just a reminder, there's 2 more events at least already scheduled, right? So one for October 27th and one for November 24th. And I think in the coming weeks, we will post the let's say the set of speakers and what we expect from it. So many thanks for participating. And many thanks to Peter Gom, Lide, and Casper for initiating this events as part of Orbit Lab and as part of the activities on our department. So hope to be able to do more of these in the future.